In this video, we're going to extend our understanding of measures of dispersion, ways to talk about how spread out our data is, by looking at cumulative frequency. Then we're going to look at percentiles, then variance and standard deviation, very, very popular. Well, all of these are popular. Then the fourth thing we'll do is take a look at how to do calculations with the GDC when you have high frequency values. So for example, if you had some data point like 3 repeats 20 times and 4 repeats 17 times, instead of typing 3 and 4 in multiple times, being able to just say, hey, this is how many times this shows up, and just calculating from that. And then I'm going to have a look at 4 exam style questions. So first we'll look at cumulative frequency, and we're going to use the same example from the last video where we can pretend that we have some stock trading strategy that has had the following returns following monthly returns over the course of 1 year. 1 month, the worst month, it lost 4%. In the best month, it gained 16%. You can see the mode is -2. The median is right here between 0 and 1, so the median is 0.5. The range, 16 minus -4, the range is 20. We could get the interquartile range too. Of course, that's Q3 minus Q1. We could calculate the mean, add up all the data points, and divide by how many there are. So this is the data that we're going to look at. Now, a cumulative frequency is just what it sounds like. It's the frequency of your data, so how often it shows up, but cumulative, as you go from -infinity and proceed to the right. Okay, and so let me start off with a histogram of this data and to help me explain in more concrete terms what this means. So I'm going to come into RStudio here. Now, RStudio is definitely not a requirement of IB. It's something that I'm showing you because it would actually make your work easier in the future. And it has some nice features that I might rely on in the future. So, so I typed in my data here. I hit Control Enter to enter it in, and you can see up here that the data has been entered. It tells me I have a list from 1 to 12, and it's a list of numbers. And I can type data and go Control Enter to see it, and down here we can see there's my data. Okay, and I could hit Summary of the data to get my 5-number summary plus the mean, right? So here's my min, my Q1, my Q2 or median, my Q3, and my max. It also gives me the mean. But what I'm going to do here is I'm going to get a histogram by typing hist and Control Enter. Here's a histogram of this data. Okay, so we see that it's positively skewed. It's right skewed because if it was to be symmetric, here, let me make this bigger so we can see it here. Oh, that's not going to show up. Okay, well, you learn something new every day. All right, so if this was symmetric and we held on to the data and pulled to the right, we would get what we actually have. And because we have to pull it to the right or stretch it to the right, that's why we call it right skewed. The skew is not where most of the data actually is. It's where you have to pull the data. All right, so that's the histogram. So you can see there's a lot of data points, 6 in fact, between -5 and 0. And let me show you what the cumulative frequency looks like by comparison. So in R, I'm going to use the command ECDF of my data. And so that gives me what we call an empirical cumulative distribution frequency. In IB, we just call it a distribution frequency. Empirical means that it's data that's been observed. And distribution, these are all distributions. So let's get a new bit of data. I'll just call it data 1. Is going to be my ECDF of my data. And now I'm going to plot data 1. Okay. So what you see I have here is I have a step function that goes up. Here, maybe I can make this a little bit bigger. This step function goes up as we go to the right. Okay, it's an increasing function. And you can see basically the frequency of having a value less than, what is this, -4 is 0. And if we flip back over quickly to our data, we can say that that makes sense because -4 is the first data point. As soon as we hit -4, our cumulative frequency jumps up to 1 because we have one data point that is -4 or smaller. And if we go a little bit to the right, you can see it's still at 1 even when we're at -3 because we have one data point that is at -3 or smaller. And then when we get to -2, it jumps way up to 4. And by the way, don't worry, this particular one is giving us a percent of our total data or a fraction of our total data rather than a count. We would normally do a count in IB. No big deal though. So it jumps up because we have now this number, 4 data points that are at or below -2. And then at -1, it stays there because we still have 4 data points at or below -1. And then at 0, it jumps up because we have 5 that are at or below 0. Okay? And here it is. And it just jumps up every time we get a new data point. So that at any x value, if we go up, it will tell us what proportion of the data is at or below that value. Okay, so it is answering the question, this cumulative frequency plot, it's answering the question, how much, I'm going to say X is all my data, big capital X. How much of this data is less than or equal to the spot that I'm at? Okay, that's what it's asking. So how much of our data is less than or equal to X. And we can answer that in terms of what fraction of the data. You can see that in this particular plot is the fraction of the data all the way up to 1. We could have percents here. This would be 0%, 20%, 40%, and so on. Or we could have counts, how many data points, okay? So that's what a cumulative distribution frequency is. Now let's take a quick look at how to do that in your GDC. First of all, I need to enter the data. So I'm going to go Stat, Edit, and I'm going to pick one of my lists to use. I can see now that this is old data. So actually I'm going to get rid of this here. I'm going to go up to L3 and hit, is it clear? Yes, clear and then enter. And I'm going to come up to L1 and hit clear and then enter. And then you can see that I already have this data in L1. So that's just fine. So I'm going to go second quit and exit. And if I wanted to double check what's in L1, I can always do that. I can go second L1, or second one to get L1, enter, and you can see it gives me the set of data that is in L1. And that is, in fact, the data that I want. All right, so now let's create a cumulative frequency by hand. So what we would do is we would list our data from least to greatest, which we already have, and we would create something like this. Along the x-axis, we're going to have the possible values of our data, okay? So -4 is the min, so -4, maybe I'll put it here, and then -3, -2, -1, 0, 2, 4, 6, 8, 10, 12. I guess this needs to be extended. 14, 16, 18, 20. Okay, and so what we're going to do is work from left to right and ask ourselves how much of the data is equal to or below this value. So how much of the data is equal to or below -4? None of it. So our graph comes like this, and then at -4, suddenly one data point is equal to or less than -4. So I have a point at -4. It jumps up to 1. How much of the data is less or equal to -3? Well, still 1. So it just comes along all the way until -2. Because when we ask the question, how much of the data is less than or equal to -2, suddenly we have 4 data points. 3, 4. So we would jump up all the way to 4. And then we come across how much of the data is less than or equal to -1, still 4, less than or equal to 0. Now we'll jump up to 6 data points. 1, 2, 3, 4, 5, 6. Then we come along until we hit the next jump, which would be at 1. So we come along here, and then we jump up 1 at 1 because 7 data points are less than or equal to 1. And we come, I don't know why this is jumping all over the place, and then we come along and we jump up because at 3 we have 1 more. So 8 data points are less than or equal to 3. And then we keep going until 5 when it increases by 2. So at 5 here, we're going to jump up to 10 because 10 data points are less than or equal to 5. 9, 10. Let's get that up to 10. And then after that, we're going to come along until we hit 8. We have 1 more data point, so we have 11 or less than or equal to 8. And finally, we have 11 or less than or equal to all of these numbers until we hit, is it 16? It's 16. So once we get to 16 here, then it's going to jump up to 12. 12 data points are less than or equal to 16 because they're all less than or equal to 16, all 12. And as I said before, we could, on this left-hand side, instead of having counts, we could have percents. This would be approximately 8%, 16%, and so on, all the way up to 100%. Or we could have fractions, 1.0, 0.08, well, those are decimals, I guess I should say, 0.16. Okay, but right now we're going to focus on counts, just counting the data. And again, what this means is, now if you want to answer the question, how much of my data is less than or equal to a certain value, you can easily do that. So if somebody gives you a cumulative frequency, and they say, oh, how much of the data X is less than or equal to 10, how much is less than or equal to 10? Well, you come to 10, you come up, and you come over, and it says, well, 11. 11 of my data points are less than or equal to 10. Okay, and to make a little connection here, if we were talking about probability, we would say the probability that a data point is less than or equal to 10 is 11 out of 12, because we have 12 total data points. Okay, but that's jumping ahead a little bit, but it's not that much of a jump, really. So now if somebody said, oh, out of all of your data, how much of it is less than or equal to 3, for example, you just come to 3, you'd come up, you'd have to be careful because this goes through this hollow dot right to this one, and over, I think that's about 8, if I've lined it up correctly. let's just see here, 4, yeah, 8. And you say, oh, well, the number of data points less than or equal to 3 is 8. That's how you can read the table. And just to go one step further, we could say the probability that a data point is less than or equal to 3 is 8 out of 12. Okay, but that's going one step further. So this is a cumulative frequency, extremely, extremely important in being one of the building blocks for various statistical constructs. Notice that this graph is always going to be monotonically increasing. Okay? It never comes down. It might be flat, but it's always going to keep going up. It'll never go down. Okay, next let's talk about percentiles. So a percentile is the percent of your data that's less than or equal to a specific value. In other words, a percentile is directly connected to the cumulative frequency. Okay? Basically, you're just looking at this, instead of looking at n, you're looking at these as percents. Moreover, Q1, Q2, which is the median, and Q3, these are special percentiles, right? So for example, Q1 is the value at which 25% of your data is less than or equal to it. In other words, Q1 is the value where out of all of your data, the amount of data less than or equal to that number, whatever it is 25%. Or in a slightly more formal way, the probability that any given data point is less than or equal to Q1 is 25%, or 0.25. Okay? The median is the value at which half the data is below it. So the median is the value, let's call it Q2 for median, where you get half the data below and half above. Or if you want to look in terms of probability, is the probability of randomly selecting one data point. If you randomly select one data point, the probability that that data point is less than or equal to the median is going to be half, 50-50, because half the data is below, half the data is above. Okay? And Q3, same thing. It is the 75th percentile. It is the value at which 75% of your data is below it. So if you were to randomly select one data point and say, gee, I wonder what the probability is that this randomly selected data point is less than or equal to Q3, well, that's going to be 75%, because Q3 is chosen to be the place where 75% of the data is below it. And if I come up to my cumulative frequency here, I can find these values. If I were to convert the y-axis into percents, this is obviously 0% down here. We're looking at 1 out of 12, 2 out of 12, 3 out of 12. So 3 out of 12 is 25%, 6 out of 12 is 50%, 9 out of 12 is 75%, and 12 out of 12 is 100%. So Q1, so somewhere here is where my Q1 is going to be. In other words, here, between -2 and 0 is where I have 1/4 of my data is below that value. And we can see that in the list itself. I think I just lost a dot. There we go. We can see that in the data itself, that at this spot, in fact, 1/3 of our data is less than or equal to -2. Okay? The median, come along here. So here it is. The median is somewhere around 0 to 1, which makes perfect sense, because when we find the middle values, it's this 0 and this 1. And then so to calculate the median, based on its definition, we get the mean of these values, the average, so it's 0.5. Okay, and as n gets large, when we have large amounts of data, we will not have very long bars here. Your cumulative frequency curve, although it will be technically a step function like this, it will just look like a smooth curve. Okay, and on the IB exams, you'll have ones where n is 200, 300, 500, and you just get a nice smooth curve. Okay, so don't worry too much about these steps. All right, well, so a percentile is basically what we've already done with Q1, Q2, or the median, and Q3, but it's just extending it to any percent that we might be interested in. So maybe I want to know the value at which 90% of my data is less than or equal to it. So I want to know for what value is this going to be 90% of my data? Or in formal terms, when I randomly select one data point, I want the probability that it's less than or equal to some value to be 90%. What is that? That's what I would be solving for. And we can get that from the cumulative frequency. So let's just do a couple of examples. Let's suppose with the data that we have, we want to know what the 30th, I don't know, what should we pick? I already did 30. How about the 60th percentile? Find the 60th percentile of this data. So that means that we want to find this value here so that we get 60% of our data below or equal to it. In other words, if we were to randomly select one piece of data, we want the probability that that data point is less than or equal to this number that we're going to find to be 60%. So we come up and we just see, okay, well, where is 60% of our data below? 60, I guess, is that, well, 60, let's, on a calculator, 0.6 times 12, that's 7.2. So we would need 7, oops, I really hate this thing. We would need 7 data points. So we come across, at what point do we have 7 data points less than or equal to a value? Well, it looks to me like it's right in here. So as soon as we hit, what is that, 1, we have 7 data points. And we can look at our list, 1, 2, 3, 4, 5, 6, 7. Indeed, as soon as we hit 1, we have 7 data points, or 60% of our data, approximately. I guess technically we would have to exceed this threshold, 7.2. So I guess technically I should really be saying that it's 3. We actually need to have 8 data points because we want to have 7.2 data points less than or equal to the number. You can't have 7.2, so we need to have a full 8 less than or equal. So we would say there that the 60th percentile is 3. Because once we're at 3, we have 8 data points, which is 67%. Or the fancy way to say that 67% of our data is less than or equal to 3 is to say that the probability, if you randomly select one data point, probability that it's less than or equal to 3 is 67%. Okay? And if we had lots of data, we could very easily get an exact number that goes exactly with 60. It's just because we only have 12 data points that is jumping around. It jumps from 50-something to 67. Okay? What if we wanted to find the 90th percentile? Or actually, let me make this nice since we have 12 data points. Let's find the 92nd percentile. Find the 92nd percentile. In other words, we're looking for the x value where if we were to randomly select a piece of data, a data point from our data set, the probability that it's less than or equal to this value should be 92. And 92 is 11 out of 12. So in other words, we want to see, well, at what point do 11 out of our 12 data points fall below? So if I come up here, I take 11, I come across, this is the point, 8. So we know that the 92nd percentile is 8 because 92% of our data is 8 or less. Okay, that's a percentile. Next, let's talk about variance and standard deviation. Now, up until now, everything that we've been talking about in terms of the spread of our data, the dispersion of our data, has been about finding specific points in the data set or ranges, whether that's the actual range from max minus min or the interquartile range, Q3 minus Q1, in the data set. Okay, so we're looking for specific spots in the data set. Variance is different in that variance is a formula based on all of the data in the data set that tries to capture, basically in essence, how spread out are the data from each other overall. Okay, that's what it's trying to measure. And standard deviation is just the square root of the variance. And there's a good reason for needing both of these measures, which we'll get into a little bit in this course. So some people have trouble with variance as a concept, but I want you to understand that we're basically looking at every data point is going to contribute some measure towards how spread out the data is. We're going to basically cycle through all of the data and see for each piece how far away is it from the mean. The further away from the mean, the more spread out your data. The closer to the mean, the less spread out your data. Okay? So, here's the formula. The variance is the mean or average of, and I'm writing this formula in a funny way on purpose. So we're going to average something. We want to get the overall average in all of our data of how far apart is it? How spread out is it? We want the average of the spread outness. And the spread outness, we're going to define this way. We're going to say the difference, right, the subtraction, the difference between the data value and the mean of the data itself. But we are going to take this quantity and we're going to square it. And there's, in fact, many reasons why we square it. I'll definitely be able to touch on one of them. Maybe I'll be able to touch on more than one of these reasons. There's kind of, well, it's an interesting question. The squaring actually makes outliers have a bigger effect on your variance than data points that are closer to the mean. Some people see this as a problem Other people see it as a feature. You know, have you heard the expression? It's not a bug. It's a feature. Maybe I'll have a chance to chat about that a little bit. But let's just focus on understanding what this quantity is first. So we're going to find the mean overall, which we call x bar, by the way. And for every data point, we want to see what's the difference between that data point and the mean. So I'm going to look at every single data point, and I'm going to subtract it from the mean, and then I'm going to square that quantity. The bigger this number is, the more distance there is between the data point and the mean. And I need the mean of this. So in other words, I need to add these all up and divide by how many there are. Okay, and this, by the way, is what we call the population variance, and that's the type of variance we're going to focus on in this course. Okay, population variance, we will put a sigma squared with a little x. That's the population variance. If you have the sample variance, you're going to use an S, but we're not going to look at that. I'm going to come over to Microsoft Excel to try to develop some intuition for you as to what's going on here. So here I've entered the monthly returns data. I can get some key statistics here. So the mean overall is going to be equals, Excel doesn't call it mean, it just calls it average. Same thing, average from this cell, colon, down to this cell, bracket, equals. Okay, so the mean is 2.3 repeating. And what I want to do for my standard deviation is, first of all, let's make these bold. I want to see how far away each data point is from the mean. So I'm going equals this minus the mean, enter. And by the way, in an Excel, I want to say in this formula that I always want that exact cell, B15, so I'm going to put dollar signs in front. That ensures that when I copy and paste, it won't change that we are subtracting B15. Now, if I copy and paste and go down like this, it updates my formula. You can see up here, or if I push F2, you can see it's moved the monthly return down to the corresponding row, but because of the dollar signs, it's subtracting off the overall mean, which is what I want. So I can actually just move this over until it becomes a black cross, double click. Whoops, come on now. Oh, I guess it's got stage fright. Okay, well, I'm just going to copy and paste all the way down then. Oh, I know why it didn't work. Okay, no big deal. Okay, so now what I have here is I have the difference from the mean, diff from mean, for each data point. You can see that 3 has the smallest difference from the mean because it's pretty close to the mean. 16 has a huge difference from the mean. This outlier has an enormous difference from the mean. It's going to contribute a lot to the variance calculation. Now, what we then do next is we square this. So the squared difference. And one reason for squaring it is because if I just average all of these numbers, the negative ones are actually going to make it look like I do not have very much variance. They're going to subtract away from the total. And it's going to make it look like this -4 is actually super close to the mean, which is not at all the case. So I want all of these to be positive values. And at this point, some people say, well, why don't we just take the absolute value? And historically, one reason was because squaring prior to computers was easier than absolute values. But in fact, there's a deeper reason. It's not just that. That's the answer that's often given. And then people will say, well, now that we have computers, why don't we use absolute values? And, you know, you could. And there is actually some development of statistics that relies more heavily on absolute values now that we have computers. But there are actually other reasons why squaring can be valuable as well, to do with other statistics. Anyway, so what I'm going to do is I'm going to square. I'm going to say, okay, I'm going to take this number squared, or times itself. And of course, it gives me a positive value. Now, if I get the black cross and double click, it fills them in. And you can see here are all my squared differences. 3, which is very close to the mean, has a very small squared difference. And as we go further away to the negative side, the squared difference grows. And as we go further away to the positive side, the squared difference grows. And this outlier, you can see, has an enormous squared difference compared to everything else. It is going to contribute the most to our variance. Okay, so we've got our differences from the mean, and we've got our squared differences. Now what we need to do is get the average of all of these values. Add them all up and divide by how many of them there are. So I can just come right here. Maybe I'll put variance here. I'll make it go to the right to look at the value that I'm about to compute. And I'll go equals average from cell D2 colon down to cell D13, bracket, enter. Okay, so our variance is, 28.6, about 29. That's how spread out this data is according to the variance calculation. The standard deviation is equal to the variance square rooted. That's the definition of standard deviation. So I'll say equals square root this value equals, so our standard deviation is 5.3. Okay, so these are two measures that sort of get at how spread out our data is. Now, the first thing I want to do is I want to just show you that there's some logic here. If this 16 wasn't a 16 at all, and it was actually a 6, then the data would be less spread out. So we would expect the variance would go down, and so would the standard deviation. Well, let's see what happens. I put a 6, enter, there it goes. So it went down a fair bit. Now notice what also happened is the mean changed, obviously. And so even the other data points, a lot of them got closer. See, let me back up. So let's take, for example, the 8 had a squared difference of 32, and I go forward again. Well, it actually got worse, 42. Hold up. Let's take, oh yeah, because it's on the positive side. It became the max, so that actually makes sense. Let's take 0. It had a square difference of 5, or negative 2, 18. And now the 5 went to 2, the 18 went to 12, because the mean shrank. And so, in fact, the calculation certainly had this data point here shrink, but on an aggregate, most of the other data points also had a squared difference that shrank. And so overall, the variance shrank, quite considerably, actually. This was originally, what, 16? So we had a variance of 28, and now it's a variance of 13. That's a substantial decrease, and the standard deviation also shrank. If all the data points were the same, well, then the variance and standard deviation would be 0, because they don't differ from the mean at all. If one of them is just a little bit different from the rest, then you can see that they all differ from the mean just a little bit, but this variance and standard deviation are very small. If I just had a few of them differing here and there, the variance and standard deviation are still quite small. If, on the other hand, I say, oh, we've got everything really spread out, you can see how the variance and standard deviation are just growing enormously. Okay, so this should give you some intuition and confidence that the variance and standard deviation reflect how spread out the data is. Let's suppose we had to calculate the standard deviation by hand. Now, let's get a smaller data set because it's a bit of work to do. let's suppose we had a nice small data set of, I don't know, let's say we have 2, 4, 6, 8. Okay, that's the data set. How would we calculate the standard deviation and the variance by hand? Well, first we'd need to get the mean. So we would go 2 plus 4 plus 6 plus 8 over 4 data points, which is 10, 20 over 4, 5. Okay, so my mean is 5. And then for each data point here, I would say, how far away is it from 5? Well, 2 minus 5. In fact, I could make a little table here. I could say this is my xi minus x bar value. Here's my xi value, 2, 4, 6, and 8. So 2 minus 5, negative 3, 4 minus 5, negative 1, 6 minus 5, 1, 8 minus 5, 3. And then I would get my squared difference from the mean. That would be a 9, a 1, a 1, and a 9. And then I need the average of these values here. That's no big deal. 9 plus 2 plus 2 plus 9 is 20 divided by 4. My population variance is 5. Now, it's just a coincidence that in this case, the variance actually equaled the mean. But there it is. And then the standard deviation would be the square root of the variance. Square root 5, whatever it is. 2.2, I think. My calculator is very slow today, which is kind of strange. Yeah, 2.24 to 3 sig figs. Notice that we actually put a squared on the variance, and that square rooting it gets rid of that squared, so it's not there. So that's actually not just notation, but it's also kind of mathematically sound. This is like it is an exponent, really. We're squaring the standard deviation. Now, what about on a GDC? Well, on the GDC, you can see that L1 has this list of data. If I wanted to know the population variance or standard deviation, I'd go into Stat, Calc, one variable statistics, and this is not what I want, so my list is actually L1, second L1. My frequency list, I just need to clear that because I don't have a frequency list here, and I will calculate. And there they are. So it gives me the mean of 2.3 repeating as expected. And right here we have sigma x equals 5.34. So that is my standard deviation. If I wanted my variance, I would need to square it. So I would square it, I get, I don't know, about 27 or something. 5.34. Let's back out of here. 5.34 squared. We get 28.5. Okay, so that would be my variance. Now, one thing that I'd just like to point out is that in this formula for the variance, because we are squaring, it changes our units. So, for example, if our units were, I don't know, centimeters, we're measuring, let's say, the length of a bunch of lumber. We have a mill. It mills our lumber into lengths, and we would like the variance to be as low as possible because we want to be able to have a standardized length. But of course, some variation is inevitable. So we have a mean number of centimeters. We have each measurement is a certain number of centimeters. So the result of this subtraction is in centimeters, is the centimeters difference, and then we square it. So then we actually have, well, an area, technically, centimeters squared, that we're averaging. That's not in the same units as what we started with. And in some cases, that can be a problem. And so part of the motivation for square rooting at the end to get the standard deviation is that we're going to square root this, and we're going to end up with the same units that we started with. Okay, so one thing to keep in mind is that the standard deviation uses the same units as the data itself. And so it's more comparable in a certain sense than the variance might be. And yet the variance does have its own merits independent of the standard deviation. So a summary of key points here. The standard deviation is just an abbreviation, which for the population we represent with a sigma sub x, or the variance. Sometimes we just call this var, especially in theoretical statistics, sigma sub x squared. These are measures of dispersion. They take into account all of the data values, and they do some calculation that compares every data value against the mean. We have that both measures are always going to be greater than or equal to 0. We have that when the measures equal 0, if one equals 0, the other one will. If one doesn't, the other one won't. If they both equal 0, then that means that there's no variance whatsoever. All of the data points are identical. And the last point here is that the standard deviation and the variance, they're very sensitive to outliers. So if you have some outliers, they will increase the variance quite a lot, which isn't necessarily a bad thing. I mean, if you have a lot of outliers and they are legitimate values for your data, it just means that your data is very dispersed. Maybe you don't want it to be dispersed, but maybe that's just the reality. Maybe it just is. On the other side, maybe those values are not legitimate values. Maybe there was a measurement error or some transcription error. If that's the case, you really better analyze whether those outliers ought to be part of your data set or not. It's a very, very important decision to make, and you want to get that right. Okay, well, what would happen if we add a constant to all of the values in our data set? So I'm just going to make an example. Well, I might as well just come back to the one we've been using all this time, -4, -2, and so on. What would happen if I added 5 to every single data point? What would happen to the mean? What would happen to the variance? What would happen to the standard deviation? Now, we can algebraically prove what would happen, but let's just take a look at Excel to get a sense. So here we're back in Excel. I have this stock market data here on the left. You can see that the mean is 2.33. Maybe I'll type that down here again so that we can refer to it. The variance is 28.56 to 2 decimal places, and the standard deviation is 5.34 to 2 decimal places. And there we are. Now you can see over here I've taken the data points and I've just added 5 to every single one. Okay, it's like if you had a histogram and you just shift the entire thing. The shape doesn't change. That's key. The shape doesn't change, but it shifts over. What do you think would happen to the mean? What do you think would happen to the variance? What do you think would happen to the standard deviation? Pause the video and think for a little bit. See what you think would happen. Okay, so I'm going to take the data and I'm just going to copy and paste this shifted data right here, and let's see what happens. Boom. Okay, so the mean went up by 5. Did you get that? It makes sense, right? If every single data point goes up by 5, then the average itself goes up by 5. How about the variance and standard deviation? they didn't change at all. They stayed exactly the same. Why? Well, because the shape of the histogram didn't change. The variance, the dispersion, the spread of the data didn't change at all. If the dispersion didn't change, then these measures of dispersion should remain the same, and they do. The only thing that happens is the mean increases if you add the exact same value to every single point. So in this case, where we add the same constant to every data point, what happens? Well, the old mean, the mean, there's a little notation that says becomes. The mean becomes the old mean plus 5. Or if you want, you can just say the new mean is the old mean plus 5. The new variance is the old variance. And the new standard deviation is the old standard deviation. The standard deviation, the variance don't change, but the mean does. Here's another question. What would happen if you multiplied everything by a constant? So this time we have the same data set, and we're going to multiply everything by, let's say, 2. So this would become a -8, -4, -4, and so on. What do you think would happen to the mean? What would happen to the standard deviation, to the variance, and what would happen to the standard deviation? Try it out if you want, or just think it through. Of course, we could do it algebraically, but I'm going to do it over here in Excel. Pause the video. What do you think? So, what happens? Well, we're doubling everything. And you can see here, I went back to the old data. The mean is 2.33. I have it copied out here. The variance 28, standard deviation 5. It's copied out so we can see what the changes are. And here in column G, I doubled every data point. Is it going to become more spread out? Well, yes. Right? The -4, the min is even smaller. The max is even larger. It's definitely more spread out. So it will have an effect on variance and standard deviation. Will it affect the mean? Well, yeah, it's going to affect the mean too. Let's put the data in and see. Boom. Okay. So what happened here? The mean doubled. The standard deviation doubled. Okay? See, it exactly doubled. The variance multiplied by 4. If I go equals D15 divided by the old variance, there we are, 3.999, and multiplied by 4. Why 4? Well, because that's 2 squared. Let's take a look at it again. This time I'm going to triple the data. What do you think is going to happen? All right, have you got your prediction? So here is all the data tripled. I'm going to copy and paste it over. And okay, so we have tripled the mean, right? Equals the new mean divided by the old mean. That's tripled. We have tripled the standard deviation. Here's the new standard deviation divided by the old standard deviation. Okay, so you triple the values, you triple the mean, you triple the standard deviation. You double the values, you double the mean, you double the standard deviation. What about the variance? Well, it's going to be times 9. It's tripled squared. There it is, times 9. Of course, there's slight imperfections because I rounded off. Okay, so if we come back over to OneNote, what have we got as a summary? Well, if you double the values, then you're going to double your mean. You're going to double your standard deviation, and you're going to quadruple, or 2 squared, your variance. If, on the other hand, instead of doubling, you triple, you're going to, triple your mean and triple your standard deviation, and you're going to times 9
your variance. And in general, if you multiply every single data point by A, then you have multiplied your mean by A, you have multiplied your standard deviation by A, and you have multiplied your variance by A squared. Okay? This example and the previous example where you're adding a constant to all the data, these are very important to make sure you know. Next, I'd like to talk about using the GDC with frequencies. So what we've done so far is we've mostly focused on looking at stat edit here. We've been looking at this particular distribution, empirical distribution of fake stock market data. And when I had -2 come up 3 times, I just typed -2 3 times. What I'm going to suggest is that you are probably going to prefer to actually do it like this. So you have -4, and in L2, you're going to actually put the frequency of that value. So -4 occurs once. So I put in a 1. And then instead of typing -2 in 3 times, what you're going to do is you're going to come into L2 and you're going to say, look, I've got this -2 3 times. And in L1, I have 0 right there. I wonder if I can clear that. No. Can I delete it? Yeah, I can delete the cell. Okay. So we have 0 then. How many times do we have 0? It looks like it's twice, but if you look back at your original one, it's actually 2 times that we have 0. So I'm going to put in L2, a frequency of 2. Then we have the value of 1. We have 1 once. And then we have 3 once, 5 twice, 8 once, and 16 once. So this is an identical representation of the same data, or it's a different representation of the data, but it's the identical meaning as before, where we just have the frequency in L2. Okay, now that we've done it this way, we can still do all the same things that we did before, plus more, a little bit more easily. So let's say, for example, that, well, let's go quit this, and we just want to see what our data is. So we go second L1, that shows us what's in the list of L1, second L2, and we can see this is the data that we have entered into L2. Okay, great. Now, if we wanted to see, for example, some statistics, we could go stat and move over to calc, one variable statistics. And all we have to do here is say, look, in L2, we have the frequency list. So the main list of data is in L1, and the frequency corresponding with how often each data point occurs is in L2. And now we can go calculate, and it will correctly calculate everything that we're interested in. You can see, again, it still gets a mean of 2.3 repeating, which is correct. It still gets that population standard deviation of 5.34, which is correct. It gets n equals 12, which is correct. Okay, and it still has our min, our Q1, our median, our Q3, and our max. Everything there is correct, okay? So now this is better for a couple of reasons, not least of which is less typing, okay? So that's a good reason in and of itself. Now suppose I want a stat plot. I can go in second stat plot. Looks like I already have the box plot on. Let's go into it. Let's suppose I want a box plot with outliers shown, okay? And then I look here, my X list, that's supposed to be L1, and my frequency, that's L2. As long as I specify those two things, I'm in good shape. So now let's go zoom 9, zoom stat, and I'll get my box plot. Perfect, and there's that one outlier, and the second greatest value is where my whisker ends there. That's a nice box plot. If I wanted, for example, a histogram, I could do the same thing. I just come in and select histogram. My X list is L1, my frequency is L2, so everything's great. Zoom, stat, zoom, or zoom stat. There's my histogram, okay? Correctly calculated based on the frequency. Now, what this also allows us to do is fairly easily now, we can also get the cumulative frequency for this data. Okay, so if I come back into stat, edit, now I want here in L3, what I'm going to want here is the cumulative sum of L2. So that basically corresponding with each element of L1 is going to tell me how many values are less than or equal to that. In other words, it's going to calculate a 1 there, a 4 there, 1 plus 3, because 4 values are less than or equal to -2, a 6 there, because 1 plus 3 plus 2 is 6. In other words, 6 values are less than or equal to 0, a 7, an 8, a 10, an 11, and a 12. Okay, so this is my cumulative frequency. And I can use this to do a bunch of things. But I don't have to calculate it by hand. Okay, so I'm going to go back and I'm going to delete what I just did. And I'm going to show you how to actually calculate it by hand. So I just pushed clear, enter, and that gets rid of them all. And now let's get it to calculate the cumulative sum for me automatically. So now what I'm going to do is I'm going to come up to the list so that I'm right up at the very top talking about the list as a whole. When I'm here, I'm just talking about the first element of the list. You can see list number 3, first element, but I want to be looking at the list as a whole. And I'm going to go, is it stat? No, it's not stat. Hold on. Stat, edit, come up to the top of the list. Is it second stat? I think that's right. There we are. Second stat. So list. And I'm going to come over here to operations. And I'm going to select number 6, cumulative sum. Okay. Whoops. Come back. Thank you. Okay. So I'm on cumulative sum and I'm going to go enter. And so you can see down at the bottom, it's saying list 3 equals the cumulative sum of something. And I'm going to say L2. That's what I want. Close my bracket, enter, and it populates this list with the cumulative sum. Okay, so you don't have to actually calculate it yourself. And memorizing this little procedure will save you a lot of grief, because if you get one little number wrong, you could mess up everything, whereas it's, of course, a calculator. It's going to do it correctly. So now that we have this, let's suppose we want to actually plot the cumulative frequency. So now to get the cumulative frequency, what I'm going to do is I'm going to get out of here, second quit. I'm going to go to stat plot, second stat plot, and I'll just go into this first one again. That's fine. Now what I would like is a continuous graph, and it gives me now a choice of my X list and my Y list. Now, the X list is the data. The Y list is what's going to be on the Y-axis, and that is going to be these cumulative frequencies that we just put in L3. So I change that to L3 and plot, zoom stat plot, and there we go. There is the cumulative frequency. Okay, now you'll notice that it did not do a step function all the way up. Instead, it actually just joined the dots. Okay, so that's one difference between ours and its. Other than that, they're identical. Okay, so you've got a cumulative frequency plot right there. Okay, so the last thing I want to do here now is go through some exam style questions. So the first question is actually going to be a follow through from the previous video. we have a group of 20 children. So a group of 20 children. They record, and I'm going to say that they're from School A, okay? A group of 20 children from School A. They record the number of hours they spent playing video games in a week, and the results are summarized in a box and whisker plot. Okay, so the min is 4, Q1 is 12. This box is way too big, actually, for the data. The median is 13, Q3 is 15, 13, and the max is 26. And we actually had a very similar question. We actually had to figure out the value of one of these values based on the range. I think we had to find the 26, or maybe we had to find the 4. Doesn't matter. Okay. And now we're going to add to this question that a different group of 30 children, so another group of 30 children, this time from School B, had the exact same survey. And for them, we know that the mean time playing was 12 hours and that the standard deviation was 2. Okay, the population standard deviation. And the question says, find the total number of hours this group spent playing video games. So the first question here is, find total hours this second group spent playing video games. Well, if we have 30 children and on average they played for 12 hours each, then we can simply multiply these two values to get the total amount. And so, I don't know why I put an X there. And so we have 360 hours total. Okay, and you can see that because if you have 360 hours total divided by the number of children, then you get your average of 12, which is what we started out with. So we're just going backwards and saying, okay, well, the average times the number of children is the total hours. Or if you would prefer, you could see it this way. The average is the sum of all the values divided by the number of values. So the sum of all the values, the total, is just the average times the number of data points, the number of children. Okay, so that's A. B says find the variance in the number of hours they spent playing video games. Find the variance. Well, the variance is quite simply the standard deviation squared. So the population variance is just going to be 2 squared, which is 4. Simple. Okay. Then the next question is to find the mean number of hours that all 50 children spent. Okay, so now we want mean number of hours for all 50 children. We know the mean for these 30 children. We know the total hours spent for these 30 children. But we're not given the mean for these 20 children, right? We're given a box and whiskers. This is the median, not the mean. So, what could we do? Well, I hope you didn't scratch your head too long because I realize I forgot to give some additional information, which is that these children spent 280 hours total, and that was given to us in the last video. So now what do we do? Well, we can see what is the total number of hours that all 50 children played. That's going to be 280 plus 360. So our sum of hours for all 50 children is going to be 280 plus 360, if I got that right. 360, yes. 280, yes. And then that means that the mean is the sum divided by the number of children. So it's going to be this result, 640, divided by the 50 children. Okay, and if we had this without a calculator, we could divide by 10, divide by 10. 5 goes into 64. 14, 2, 10, 4, bring down a 0, 12.8. Okay, 12.8 hours on average for the 50 children altogether. Then the next question is part D. The next week, there was an exam week in School B. Okay, School B has an exam week. What happened? Well, the children were studying more and playing video games less. And so what happens is all the children spent half as much time playing video games. Okay? This is all the children in School B. They want us to find the mean hours they spent playing. Find mean hours spent playing and the variance in the hours spent playing. And this is where the facts regarding adding a constant or multiplying by a constant come in very handy. So we know that if we add a constant, then the mean goes up by that constant, but the standard deviation and variance do not change. We also know that if we multiply by a constant, then the mean is multiplied by the constant, the standard deviation is multiplied by the constant, and the variance is multiplied by the constant squared. So in this case, what's the constant? Well, the constant is 1/2. Every child spends half as much time playing. So what happens to the mean hours spent playing? They get cut in half. So if we come up to the mean for this group of 30 children, instead of it being 12 hours, it's going to be 6. And the standard deviation, instead of being 2 hours, is going to be 1. Okay, so the mean nu equals 1/2 times 12, which equals 6. The standard deviation is going to be 1/2 times 2, which is 1. And then the variance is the standard deviation squared, which is going to be 1. So that would be a correct solution. If you wanted to do it another way, you could say that the variance is 4, but then the variance at 4 is going to have to be multiplied by this constant squared, which is 4 times 1/4, which again is a variance of 1. So the new variance, I'll just put variance nu equals 1. Okay, either way we do it, we get 1. All right, that's the first question, exam style. Here's the second exam style question. In this one, we have, let's see here. Okay, I didn't put a number. I'll just put a number here, number 2. In this one, we have 800 students in a race. They're going to do the 100 meters. And these students all took between 9.56 seconds and 12.61 seconds to complete the race. Okay, so the fastest was 9.56, the slowest was 12.61. And then they tell us that the first 50 students win a prize. And here comes the question. Given that a student takes between 10 and 12.61 seconds, so given a student takes between 10 and 12.61 seconds, find the probability that they won a prize. In other words, this student is not between 9.56 and 9.99. Okay, the student took 10 seconds or longer, or maybe they were dead last. If we randomly select a student out of this group, what's the probability that they win a prize? And along with this question, we are given the cumulative distribution function, which I have put here in R. Okay? So, what we have to do is say, okay, this student is somewhere between here, 10 seconds, and the very end. So in other words, he's not, or she is not one of these first few ones. So we have to see, what does this line up with? Now, on an exam, you're going to have grid marks that make it much more clear where we line up. You're not going to have to just eyeball it. And what I'm going to do to make things easier here is I'm going to put some lines. Let's go AB line. Let's see if I can get this right first of all. 0.1 comma 0. Let's hope this is right. Yeah, that's right. Okay. 0 AB line 0.05 comma 0. AB line 0.03 comma 0. Okay, so if you look in there, it looks to me like 10 seconds lines up with 0.03. What does that mean? That means that this student is not among the top 3% of finishers. He or she is among the bottom 97%, which is most of the school. But we know for sure that this student is not among the top 3%. So how could we figure this out? Well, the top 3% is how many students? Well, it's going to be 0.03 times 800 students in the race. If I use a calculator here, or I could do it longhand, I get 24. Okay, so this student is not among the top 24. This student is somewhere between 25th place and last. And the question is, what's the probability that this student wins a prize, given that information? Well, we don't know in what position this student ends the race. It could be anywhere between 25th and 800th. So there are 776 positions that this person could be in. When you're trying to find how many numbers there are between two numbers, including both endpoints, the formula is you subtract them and add 1 if you're including both endpoints. If it's the number of jumps between them, you don't add the 1. So here I get 776. And okay, so he's one of these 776 students. How many of these students are going to win a prize? Well, 25th through 50th, that's 26. So if we randomly select a person between 25th and 800th, the chances that we select somebody who will win a prize is 26 out of 776. Or on a calculator, that is 0.335, 0.0335, or about 3.35%. That's the likelihood that this person, or probability, likelihood is actually technically different. This is the probability that that student wins a prize. Follow-up question. Find the 60th percentile. Okay, so we'll come back over. Oh, I just did all that without showing you. Sorry, here's the work I did in OneNote. So I just said that this person came in between 25th and 800th because the 3% that had a time faster than 10 seconds makes the first 24 finishers. And so this person comes in one of these 776 spots, and of them, 26 spots win prizes, 25, 26, 27, 28, 29, 30, all the way up to 50. Or we could go 50 minus 25 plus 1, right? Because you subtract them and add 1 when you're including both endpoints. And so there are this many spots to win prizes out of this many possible spots where he might be, which works out to 3.35%. Next question, find the 60th percentile. So we'll come back over to R. We're given this cumulative frequency, and we want to find the 60th percentile. Well, that lines up with this here, 0.6. That's going to be the 60th percentile once we find out where that is for x. So what I'll do, again, on an exam you'll have nice lines. I'm going to put AB line 0.6, 0, 0.6, 0. Okay. And by my eyesight, that appears to be about 11.15. Let's try that. So now I'm going to put an AB line vertical at 11.15 and see how close I am. Pretty darn close. So I'm going to say then that the 60th percentile is at a time of 11.15 seconds. So the 60th percentile occurs at a time of 11.15 seconds. Okay. Number 3. A data set has a mean of 25 and a standard deviation of 4. It turns out that all of the data points should have had 100 added to them. Maybe the research assistant took a shortcut. Instead of putting down 114, 116, 124, 118 every time he recorded the data, he just put the last 2 digits and decided he would add 100 later and forgot to do so. Okay, so we did the calculations, but everything needs to have 100 added to it. Question, how does the mean change? How does the standard deviation change? Answer, the mean becomes 125 because 100 is added to everything. The standard deviation does not change because the shape, the distribution, the dispersion doesn't change. Okay, so it stays at 4. Question number 4. A data set has, again, a mean of 25 and a standard deviation of 4. Every data point is multiplied by 12. Okay, maybe that's done to scale it to a new measurement. Maybe everything was measured in feet and we want to scale it now to be in inches. What is the new mean? What is the new variance? Well, in this case, the mean will be multiplied by 12, 25 times 12, which is going to be, I think, 300, if I have that right. Yeah, that's right. And the standard deviation will also be multiplied by 12, so it will become 48. The variance, on the other hand, will be multiplied by 144. So the old variance was 16, because remember, the variance is the standard deviation squared. And it's going to be multiplied by 12 squared, which is a whopping 144 times 16, 2,304. Okay, so there we are.